So I'm hopeful we're going to get at least a few more people in. But I may as well do introduction. Aldo has been researching here at CIIMAR, I think, for over a decade now. And from my understanding, you've been working with chemostatic and sort of continuous production systems for microalgae. Anabe-san is working with Euglena, which is a company in Japan that also uses microalgae for making its product.
Nice to meet you.
Yeah, thank you very much. That's right. Nice to meet you.
So I apologize for the short notice. I know that we only sort of finalized the plan in the last week or so. But we are recording this session. So if there's anyone else that's not being able to attend, they should be able to get a copy. Yeah. Okay. Let's just get this kicked off. So thanks again for joining. And thank you, Aldo, for coming to present the results of the study that we did. The study was funded by BlueBio Alliance, who may also send someone to join a bit later. But yeah, so the study was looking at using microfluidic system for cell retention in a long duration perfusion culture system to see how that would impact the growth and potentially viability of Scenedesmus species of microalgae. And with that, I'll let Dr. Aldo Barrero kick off the presentation.
Well, thanks a lot, Brian, and it's a pleasure for me to be here to present these results of this really interesting system. And so I'm going to share my screen immediately. So first, this work that I entitled like a study of the performance of the photobioreactor with continuous perfusion for microalgae biomass production was made in collaboration because of a collaboration mediated by BlueBio Alliance between the UF8 from the company which Ryan is from, and CIIMAR, which is my research center. And then here we see a schematic vision of the structure of a photobioreactor with continuous perfusion. Basically, it is a normal photobioreactor with continuous flow, in which the flow that goes, there is a flow that goes from outside the culturing flask that is diverted into two branches. One goes back to the bioreactor flask, another one goes to the waste. These two branches, in the middle, in between these two branches, there is a tip that is the one creating this microfluidics system that diverts the flow into one that goes back to the bioreactor with more concentrated, is concentrating the cells from the culture, whereas the other one goes straight to the waste without most of the biomass of the microalgae. As a result, the concentration of microalgae in the bioreactor is increased in a continuous way. So it's continuously getting a concentrated flow of microalgae. So our aims were to study first to track the cell biomass production until a steady state in the system, to see if it is stable, if it's reaching high levels, and then also to study if the time to reach a steady state, like the top of the biomass, are possible with this system, would be faster or not. Based on this principle, there is a concentration, a permanent reconcentration of the microalgae, of the biomass. And then how is the potential, more or less, of the system to be intensifying this process? If the flow concentrating the microalgae biomass can be somehow be intensified in the sense that could be more concentrated or stronger in terms of biomass production. And then if there are any issues or any interventions that are needed in order to keep the system going for a long term, which are the problems associated, the potential problems associated with this. So then the research plan was basically tracking the microalgae biomass in a long-term operation of the system, 45 days. This was just a bit limited by our by the schedule of this project, because otherwise it could be staying for an indefinite period of time, not just 45 days. And then during this time, we would estimate the maximum cell growth rate, the biomass yield, estimate the time to reach a steady state, which I call it like this, but this could be for other people. They might understand it better if I say the recovery from harvesting of biomass, but essentially it's the same thing. And then to get a comparison of all these numbers, of all this performance, with a standard continuous photobioreactor with a normal flow that goes straight to the waste without reconcentrating the microalgae. So these were the conditions in the laboratory. So we were growing the system limited by nutrients. So this is the nitrate to phosphate ratio and the micromolar concentration. In general, this is a low, relatively low concentration, in the sense that you cannot get the system limited by light under these conditions. But however, the system was potentially being limited by CO2, and we solved the problem of CO2 limitation by tracking the pH and adding, increasing the bicarbonate in the medium. Then we were measuring cell abundances on a daily basis. The culture flask was half a liter of culture, and the microalgae strain was a species and not determined species of Scenedesmus that you can see here. So this is not our strain. Ours is a bit smaller, but the appearance is the same. It's like a normal, a typical Scenedesmus. And this is a picture of how the system looks with our setup. So here in the middle, with the green microalgae growing, is the flask, the culture flask, with containing the Scenedesmus. Then on the left, you can see the flask containing the fresh medium that through this peristaltic pump that you can see here in the back is being pushed towards the flask of the culture. And then you get here the flask of the waste, where the waste has an outflow from the culture, and this outflow, which is pumped by this pump over here, it goes first through a filter, that is a small filter that you can see here, in order to avoid big particles to get into the pump, and then it comes out from the pump. It goes into the pump through this connection here. It gets out of the pump from this tube, and then it goes straight to the tip. So this is the tip that is the main, the most important, the critical thing of this system. When the flow enters in the tip through this connection, then it is diverted through two branches. And by this microfluidics effect that maybe Brian could explain better than me, one branch goes back to the original culture, concentrating the cells, and the other branch is showing a more diluted medium and goes straight to the waste. So this microfluidic system, what it's doing is actually reconcentrating the cells towards one of the branches. And actually you can see it very clearly here, because in the waste you don't see almost any color. Well, there is a tiny color because there are some cells that you will see later in the results. But mainly what you see is a completely clear, really clear flask. Sometimes, well, there are some cells, and after long-term running, some of them are growing, so you see them in the bottom growing here. But actually, this was one day I was working very well, the system very fast, so the waste was quite filled without any, well, there was no time for the cells to grow, like in a couple of days or two. So then these were the results of biomass development during 33 days. So you can see how the steady state was reached here. It took more time, as we'll see later, than usual to reach steady state. And this is because at the beginning, of course, we have some problems of adjusting the system in terms of the flow there. We couldn't control what we didn't know actually how would be the flow of the reconcentrated brands that goes back into the culture. So we need to adjust basically the speed of the peristaltic pump to the flow that was governed or driven by the chip. So at the beginning there were some problems that were delaying the normal working of the system. Then also here there was a bit of high pH above 9, which is an indicator of CO2 limitation, and then is when we need to add to increase a lot the sodium bicarbonate concentration in order to reduce the pH below the limitation, and only then is when the algae were able to reach the steady state. So a few numbers out of these results are the apparent growth rate. The maximum apparent growth rate estimated like in the proper way gives 0.97 per day, which means a doubling time of 18 hours. Well, this is a lot. I call it apparent because I'm not taking into account the dilution rate of the system. So actually the actual growth rate is actually bigger than that, like it's larger than this. The thing is that, well, I didn't take into account the dilution rate because, as I mentioned before, at the beginning the dilution rate was unstable, right? We were changing it in order to adjust it. So we didn't measure it instantaneously. So then it would be a bit useless to calculate the dilution rate of the system. Anyways, for comparison purposes, with a normal, with a standard continuous photobioreactor, this is fine. Then I also taken this number here because this was the maximum apparent growth rate observed one day. It was one day when actually the system was working really, really well. The reconcentrating flow into the culture, and as you can see, the apparent growth rate was huge, like something, of course, much higher than what could be expected for this species, with a doubling time of 8.5 hours. So this is, I call it, keep in mind that it's always apparent, not only because of the dilution of the system, but also because obviously here the cells are being reconcentrated, so they don't grow as much as it seems. Then another short experiment, well, that I repeated twice for the what I call the time to reach steady state, or if you prefer it, it's like equivalent to do a recovery from harvesting. So basically, it is calculating how much time does it take to reach the saturation of biomass. I did a, well, this was a bit random because of the conditions that I had in the experiment. So I was trying to use two initial abundances. So first, the steady state one was starting from more or less 10% of the biomass at the steady state, and the second was starting from 40%. So it's like, imagine if you do some harvesting and you reduce the biomass concentration 10 times or a bit less. And then in these cases, the difference was like a couple of days to reach steady state from 6 to 4. And in principle, this seems like a lot, right? Compared to I mean, a lot, sorry, really, really fast compared to a standard bioreactor. Then, well, the fit of the parameters here yields 3 million of cells per ml in a steady state. I will talk a bit more about this later. And the growth rate and the, well, the growth rate and the inflection point is a logistic model, by the way. So it's indicating a really, really fast growth compared to what could be expected in a normal system. So then this is the performance of the flow created by by the chip, the diversion of the perfusion culture and the waste. So here we were sometimes facing some problems, and it's because, as you can see, well, this is indicating the percentage of cells that were found in the perfusion. So the perfusion is the flow that goes back into the culture. So the flow that is reconcentrating the biomass in the culture, and the waste is the flow that goes straight to the waste. So the average concentration in the perfusion was 130% relative to the culture, and the average concentration during all this period was in the waste was 11%. So apparently the success was quite good, but here you can see that it is quite irregular, but not very constant. The reasons for this is they have to do with, I think, with the setup that we did in our lab, and this can be improved a lot from my point of view. And the main problem here was the growth of the microalgae in the tubing system, because I think that one of the problems was an excess of tubing that we have in our system. All this can be set up with some alternative designs of the photobioreactor with less, let's say, less meters or centimeters of tubing, through which all the flow needs to go with the cells. And then the problem is that the cells, they grow in the tubing. And even if we had, if you remember in the previous slide, from the picture of the system, there is a filter aimed to control or to eliminate the flow of particles through the pump. But this filter is, if I remember well, a 60 micron filter or 75 or something like that. And obviously the cells go through the filter. And the problem is that these cells, they grow in aggregates, and then they, at some point, they start growing attached to the tubes, form aggregates, and then in the end, the particles from those aggregates are larger than what the filter allows to get through. So in the end, the solution that I found was replacing the filter regularly. So all these arrows that you see here were time steps in which I was replacing the filter. In one of them, this one here, I was even replacing the whole tubing system. Replacing means like putting a new one autoclave and clean in the system. And you can see how after every change of filter, there is a clear reduction here, of course, here as well, here, and all the time, there's a clear reduction in the concentration of cells in the waste, and an improvement on in the concentration of cells in the perfusion. So this was probably the main limitation that we find in our system for a long-term, run in proper conditions. So I think with a better design of a few details in the setup, this can be greatly improved. And actually, I think like concentrations above 150, which were found at certain time points, could be like made more regular. So the performance of the system, I think, with a few design and technical improvements, can get much better. Another comment that I would make here is that by chance we also found that the chip that was autoclaved, like the whole system before starting experiments, the autoclaving was distorting a bit somehow, we don't know how, but it's distorting a bit the structure of the chip. And then after autoclaving it is not so efficient as before. And I found it by chance because I was trying to do the steady state experiment without autoclaving, because we had very few days left. And actually I realized that the performance was so good that I couldn't even fit it to the peristaltic pump that we have in our lab. So the system was running so fast that the peristaltic pump was not efficient enough on our tubing to replace the volume that was removed from the culture to the waste. So then I needed to autoclave the chip, and then it went back to working, let's say, slower than original. So slower means something like this, right? So I think that thinking about potential small technical details that could be changed this could be really improved. And then we are still missing, this is to finish, a proper real comparison with a standard nutrient limited continuous photobioreactor. But for now, I did a theoretical comparison of both. So under the same conditions, like the average concentration or reconcentration of cells observed in the perfusion, and with growth parameters similar to our Scenedesmus strain, what could be expected for our Scenedesmus strain. And surprisingly, I was surprised at these results because a priori, I was expecting that the reconcentration, the continuous perfusion, would reduce the level of nutrient so that at some point the population of microalgae would be crashing or having troubles. But actually, the model showed me that this is not what is going on. What is going on is that the continuous perfusion is introducing a new equilibrium, a steady state, that is characterized by a lower nutrient level, so the nutrient is consumed more efficiently, and a much higher cell density. So this is a plot showing the simulation on the model, and you can see in the discontinuous line is the microalgae growth in the continuous perfusion system, and the continuous line shows the macroalgae growth with the standard continuous photobioreactor. So as I'm saying here, the increase in biomass of the perfusion system compared to the standard bioreactor is by 70% more, right? You can see here the level at the steady state, and here how they differ by more than twice. And then the days to reach a steady state, starting from 1% steady state on its case. So, well, you barely see it here, but there is a difference in the discontinuous line compared to the continuous. So they start after, well, I ran a first simulation to see how was a steady state, and then I restarted the simulation, setting 1% of steady state for each of the systems, and you can see how the difference is also like less than more than one half for the days to reach the top of biomass production. So it's quite obvious from this picture. So all this, well, it's would confirm more or less the numbers, what the numbers that we got are suggesting, but we still need to run the standard system under these conditions to compare. So here, well, we can say that the fits of our data to this model are quite good. We didn't run our system from 1%, starting with 1% of steady state, but the total biomass that we reached was like just a bit lower. If you remember, well, I can show it later, but this is predicting a steady state of around 4 million of cells, and what we found in our culture was a bit above 3 million, around 3 million. So it's a bit lower than what the model predicts, but obviously this model contains some parameters that are real, but others they are more or less estimated. So the match between model and real data is quite good. For the standard system, I only have guesses, but in principle, I work with Scenedesmus, not in this setup, but a very similar one, another lab. And under similar conditions, this prediction of 1 million seems quite accurate, at least from my past experience. Of course, we need to confirm it, but the predictions for this difference shown by the model seems like to be really accurate, according to my previous experiment. So in the end, the system looks really promising, just for well, different applications. Obtaining a really high or more efficient consumption, based on a more efficient consumption of the resources, a really high biomass production of algae that is sustained for an undefined period of time in the long term, and also reaching this biomass much faster than in normal systems, and also, well, for other kind of applications, it could be interesting to simply get the clean medium from the waste is out the cells, or with a really low concentration of cells. That could be useful for sometimes obtaining or purifying or compounds are released by the microalgae. So I think it's a really promising system, and also in the very short term, it shows a really good performance in the concentration. In terms of 1 day only, or 2 days, you see how the biomass concentration, it is always exceeded by a lot what the normal systems can do. So in principle, I am thanking here all my colleagues from my lab, that Joana Moreira Silva, for all this all the administrative work on this, Raquel and Joao for providing this training, and then BlueBioValue Alliance with Mariana for getting in contact, CIIMAR with UF8, and of course Brian for all the support and all the work that we did together at the beginning of the system to set it up. Obviously, without him, it would be impossible to do any kind of test here. So, okay, so this is it, and I'm waiting for your questions.
Okay, thank you so much, Aldo. Yeah, so I wanted to just point out, you did mention it in the presentation that we experienced a CO2 limitation relatively early on, before we started monitoring the pH. But do you think that has implications for, let's say, where microalgae facility is co-located specifically for CO2 capture? Could that be potentially another application space where they would just see a higher uptake of CO2 being passed through the system?
Yeah, that would be another application. I'm not strongly familiar with this kind of systems, but of course, the way I had to deal with CO2 limitation was adding sodium bicarbonate, but most often this would be done by increasing the CO2 concentration in the air inflow.
Yeah,
and it's much better. That is better for any scale. It is just that in our lab we didn't have the facility to do it, but then I do like the simpler way. But obviously, it will be much better to do it by increasing the CO2 in the inflow. And yeah, that could be another application as well to increase the CO2 sequestering.
okay.
Mm-hmm.
Would anyone else like to ask some questions? Okay, if not, I'm gonna dig in a little bit more to the recovery. So that's new data to me. I know you've been sort of giving me reports as we go along. So when you're saying you're starting at 10% of the steady state concentration, and it's recovering in about 6 days. Is that the steady state from the perfusion system, or from, let's say, a standard chemostatic sort of system?
From the perfusion. Mm-hmm.
Okay, so that would already be, let's say, a higher population of cells relative to the sort of standard chemostat steady state. If we run the numbers, it would be about.
No, it's it was around 300,000 cells per ml.
Okay.
Because the steady state, it was well, the model was showing it was 3 million almost.
Yeah.
It was like around 300,000, so like 10%.
Mm-hmm.
And so it was that. So
that would be about a third of the predicted steady state of the standard system.
The predicted steady state of the standard system was 1,300,000. Mm-hmm.
Yeah. Okay. And I guess that means that potentially, if you were to do sequential harvesting, you could take 90% of the total reactor volume every 6 days, and that would lead to a certain level of productivity that just wouldn't be matched by the standard sort of system.
Yeah, that would be the thing. Yeah. Yeah, the numbers that I got were I didn't decide it. They were based because of the limitation of time. Basically, I needed to do what I could do.
Of course.
So I restarted because it was all this, the complications here were all this thing of trying to set up the pump speed and to the right and getting the right data. So
And change the filters out and
so in the end, I could do it with 10% and 40%. 40% perhaps is a bit too much to this test, but the 10% is perfectly okay. So basically, you can remove 90% of the biomass, and then it will recover in around a maximum of 6 days. In this case, in our condition.
yeah, in these conditions. Okay.
And it will be in a standard system according to the model simulation. That will be more than double. So, which actually I don't need a simulation to do that because based on my experience, steady state in a normal system, it takes a minimum of 15 days or 20 to happen. So,
Okay.
6 days is much faster. It's really fast.
So now, of course, this was just done in at the lab scale, but we're looking to implement a system that could do this at the sort of large volumes, maybe 10,000 liter reactor volume scale. But it's quite a challenge and quite a commitment. So.
Yeah. Yeah, well, I think the numbers are going to be, of course, the larger scales need some specific technical adaptations, but the numbers are there. So
Yeah. Okay. I was hoping we could maybe get a question or two from the other attendees. Anything you'd like to learn more about?
Well, I'm not really from this area. I'm more for a biorefinery area, which is after the harvesting. And probably I will want to understand better the cell stainer that you use. It's a polymer filter kind of, or?
So the microfluidic chip itself is, in this case, made of mostly PMMA and SU8, and it's made using photolithographic techniques. But that's just because it's relatively easy to get those produced at the sort of single chip level in that way. But what our company's done is taken that and translated it into a precision stainless steel fabrication method. So the actual channel itself is around 75 microns in thickness. And then it has sort of unique geometry, which migrates cells using a number of phenomena in the flow to one side of the channel before splitting it off. And that's how this, let's say, cell retention or cell separation occurs. It can get quite technical, so I won't go into too much detail. But essentially, we have one inlet where the dispersed population goes in. All of the particles or cells, in this case, over a threshold size, get moved to one side, and then the flow is separating media, which is clean of that size, and then all of the population going out another output. Yeah. So does that explain a little bit more about what's happening there and how we look to scale that to a more industrial use case?
Yeah. Thank you.
So yeah. Okay. I guess another question would be, Aldo, you've worked with Scenedesmus before several times. Now, obviously, we were kind of constrained by the size limitations on the specific chip we were testing. But would you expect this to translate well to something like a chlorella, which is maybe more commercially produced, or a nanochloropsis, if we were able to provide the chip that could do the same job?
Yeah. I'm absolutely convinced. Yeah, I will work with. I don't see any problem with that with the size of the species. If the chip can be adapted to that, I think it would translate perfectly and work and operate perfectly as well.
Okay, so really,
A different in size. Chlorella is not that different in size relative to Scenedesmus. It's a bit smaller, but it also forms aggregates. So.
okay, sorry, I got lost a little bit in my head there.
So you
have-
hear my answer? Or not?
I did, yes. You think it would translate well so long as the chip could be adapted to separate at the correct size.
Yeah.
I was thinking in terms of like the growth rates of smaller species typically is faster anyway. I guess I can see the potential where you might get that regrowth down to maybe a couple days even for something like a Nanochloropsis or and that could just pump out just a really intense amount of biomass.
Yeah. Like with fast-growing species like Nanochloropsis, obviously all the times are going to be reduced. Like so it's going to produce a lot of biomass really fast.
And sequester a huge amount of carbon dioxide really fast as well.
Yeah.
Interesting.
It can be adapted to that. Yeah.
Cool. I think it would be great to be able to go out and make that happen. I guess what we're seeing really is that the work that's been done in sort of biopharmaceutical industry where perfusion is used more often commercially, it really can translate directly into the culture of other types of cells, basically suspension culture. Yeah.
Well, I think that for Chlorella, the same chip should work without any modification. I would expect for Chlorella.
Okay.
For maybe we need to adapt a bit the size, but for Chlorella, I'm sure this same chip will work as good as for Scenedesmus.
Okay. Excellent. I'll put out one more opportunity for questions from the other attendees, and if not, I guess we can call a close. All right. Well, thanks again for your time. And as I say, this has been being recorded. If anyone would like a copy, please get in touch. Yeah. So I hope you have a great day.
Yeah, I can also send the presentation if anybody wants the presentation to have more present the numbers.
Okay. Thank you very much.
Thank you.
Hey, thank you.
Thank you. Bye.
Thank you very much.
Thank you.
Thank you.